Hi everyone, it's Mr. Grant here. Today we're going to look over the main topics from this unit on thermochemistry. Thermochemistry deals with the energy associated with chemical reactions. And this topic is more relevant than ever now that we are using more energy in our daily lives than any other generation before us. In this unit, we learned ways to predict the energy change associated with reactions. The first method involved using the formation enthalpies of the substances involved in the reactions. We learned that the enthalpy change of a reaction equals the sum of the formation enthalpies of the products minus the sum of the formation enthalpies of the reactants. So let's look at an example, the combustion of CH4 or methane in air to produce CO2 and water. In this reaction, we have two reactants, CH4 and O2, so we would need the enthalpy of formation for each of these. For O2, we would then need to multiply its formation enthalpy by 2 because we have 2 moles of O2 in our balanced equation. However, this becomes a moot point ultimately because O2 is an element in its natural state. The formation enthalpy of all elements in their natural states is 0. If you consult a table of formation enthalpies, you won't find O2 or any other naturally occurring elements on there because it's assumed that we know they're 0. We have two products as well, CO2 and H2O, and again, we need to multiply H2O's formation enthalpy value by 2 because we have 2 moles of H2O as products. Putting this all together, we will need to sum the formation enthalpies of our products minus the enthalpy formations of our reactants. And I'm not including O2 here because it's 0. We could then plug in these numbers by looking up the values of the formation enthalpies from a table, like so. You could pause the video now to see if you could find the values that we need from this table. Okay. Note that water is listed twice here. One value is for gaseous water and one value is for liquid water. So unless otherwise stated, we assume the reaction involves liquid H2O, which is its state at room temperature. So here you can see the value for CO2 was negative 393.5, liquid H2O was 285.8, and CH4 was negative 74.6. Working that out gives us a final enthalpy of reaction of negative 890.5 kilojoules per mole. This means that if we burned 1 mole of CH4, which is 16 grams of CH4 using the molar masses, it would release 890.5 kilojoules of energy. And that's a lot of energy for a small amount of fuel. Another thing to note is this value is not an estimated enthalpy change, it's exact. Assuming we're using the correct equations and formation enthalpies, this reaction should release 890.5 kilojoules per mole. A second method to find the enthalpy of reaction, which we can use even if we don't have the formation enthalpies of all the reactants or products, involves using bond energies. The enthalpy change of a reaction is the difference between the bond energies of the bonds broken in the reaction and the bond energies of the bonds formed. Okay, so let's look back at our original reaction involving the combustion of CH4. Here we can see our reactants drawn to show the bonds. Our reactants contain the following bonds and must be broken during this reaction. We have 4 CH single bonds and 2 OO double bonds that will need to be broken so these atoms can be rearranged. Our products contain 2 CO double bonds and 4 OH single bonds in total. These are the new bonds that form during this reaction. So, putting this all together, the enthalpy change of this reaction can be found by summing up the bond energies of the bonds broken, which would be 4 CH single bonds and 2 OO double bonds, and then subtracting the bonds formed, which would be 2 CO single bonds and 4 OH single bonds. 2 CO double bonds. So we could look these values up on a bond energy table. Again, you could pause the video here if you want to see if you can find these values on your own. The CH single bonds require 413 kilojoules per mole to break, and the OO double bonds require 495 kilojoules per mole to break. These values are positive because we would need to input energy to break bonds. We then subtract 799 kilojoules per mole for each of the two CO double bonds because energy is released when bonds form. Similarly, we subtract 463 kilojoules per mole for each of the four OH single bonds because those are also being formed in this reaction. Okay. Doing the math gives us a final enthalpy change of negative 808 kilojoules per mole. This is a little less than what we found earlier, which was negative 890 kilojoules per mole. So unlike the previous method of using formation enthalpies, this prediction method is only approximate, but we're still within 10%, and oftentimes we could be even closer. This method is also more flexible because we don't always have the formation enthalpies of all of the substances involved in the reaction, but we can often estimate bond energies, even for complex molecules. So I hope this helps. Let me know if you have any questions. Have a good one.